Hi guys, my name is Avezan Logde. Today in this video we will be discussing about the post-synthesis simulation. Before moving that, we will be seeing what we have been done in the previous video. In my previous video I have discussed about the behavioral modeling in Verilog synthesis, performed a synthesis on a Verilog file which was an ALU and also generated a gate level netlist. We have discussed that. So post-synthesis simulation, it is a verification of the functional correctness of a design after it has been converted into gate level netlist. So it basically says that the netlist which we generated is same, logically same as the RTL, and is it fault free. We will be checking this. It is also referred as gate level simulations. So the post-synthesis verification can be done using two methods. One is simulation based and other is formal method. So in simulation based is like nothing but a test bench. We will be writing a test bench. So it requires a test vectors. A test vector simulates the design and the output response compared to the expected response for the finite given states. So we may not catch the corner cases. It is more challenging. So when we say about the formal methods, it does not require any test vector. We will mathematically prove the logic correctness and find a counterexample. In this, we will be having a completeness in verification, and it is computationally challenging. So the formal methods are functional equivalence checking and boundal model checking. So in functional equivalence checking, we will compare the RTL versus the netlist for the given same input for functional equivalence. And then there is bounded model checking. In bounded model checking, it proves the properties of a design for limited time and clock cycle. So the satisfiability test is one of the example of the bounded model checking. In satisfiability test, it continues until we found a counter example or a problem in the logic. So basically it has some number of clocks, and the number of clocks gets incrementing with respect to the with respect to the test we are doing. So let's do a Yosys demo on this. So let's do the formal verification in Yosys. Firstly, we will move to the directory where we have saved the files. Then we will open Yosys. After opening, we will be providing the inputs to the Yosys, which is read Verilog. In this, now we will be providing two inputs, which will be our RTL code, which is ALU.v, and the second will be the netlist we've generated. So before doing, we'll be doing one prep and the module name ALU. So found zero error, then we'll do design dash stash gold. We'll save the design with the name of gold, and then we'll again do read Verilog, and this time we'll be giving the second input, which is our netlist. After that, we'll be doing the same steps, same module name, and then we'll store this design also. For this, we will be giving the name gate, because in Yosys, when we do the equivalence checking, the default names for the two given files should be gate and gold. So now we will fetch the both files. First gold as gold and the module name ALU. Similarly, we will be doing for gate. Okay, now we have called the two modules, which are gate and gold. So the gold is for the RTL code and the gate is for the netlist. Now we will check the equivalence between both. So gate gold and equivalence. So presumably equivalent wires, A gold, A gate, which is A. So let's move. Now we will again do prep and equivalent. So zero errors. Then we'll just do a simple equivalence checking and trying to prove okay success. So it shows that proved 16 previously unproven equivalent states. Let's see the status. So in status found 17 equivalent cells of those 17. So all states are equivalent for both the RTL and the gate level. So the netlist we have generated is correct for this. So there are many different steps. So we have seen the Yosys demo. So in Yosys actually we can only see the equivalence checking. We cannot see the bounded model checking. We need some commercial tools for doing that. So currently I don't have any. So there are more different design verification methods such as static timing analysis for the timing verification, then design for testability. Then we have ATPG, which is automatic test pattern generation. Other than that, we have BIST, which is built-in self-test and power verification. All these tools, all these methods require some different tools for that. So we can perform STA in OpenSTA and DFT in some commercial tools, and ATPG based also we need some commercial tools like Cadence and Synopsys. So this is for the today's video. Hope you like it. Thank you.